Hello and welcome to all students. In this lecture, we learn about congruence relation on Z, and we discuss about some problems on congruence relation on Z. Okay, so outline of our lecture is some introductory part, and then we see some examples on congruence relation on Z. In this lecture, we solve some problems on congruence relation on Z, and these problems are based on properties of congruence relation. Let us take example number 1. If A is congruent to B mod n1 and A is congruent to B mod n2, and if n1 and n2 has GCD 1, then show that A is congruent to B mod n1 into n2. Okay, so in this problem we have given that A is congruent to B mod n1 and as well as A is congruent to B mod n2 also given that the GCD of n1 and n2 is 1, and we have to show that A is congruent to B mod n1 into n2. To show that A is congruent to B mod n1 into n2, we just have to show that n1 into n2 divides the difference A minus B. Okay, just we have to show this thing. If we are able to show that n1 into n2 divides the difference A minus B, then we can say that A is congruent to B mod n1 into n2. Now how to show we will see now. So let us write the solution of that problem or answer. Given that A is congruent to B mod n1 and A is congruent to B mod n2. As A is congruent to B mod n1, by definition of congruence relation, and this implies that n1 must divides difference A minus B. Also given that A is congruent to B mod n2, therefore n2 must divides difference A minus B. Therefore, there exist two integers k1 and k2 such that A minus B is equal to n1 into k1 and A minus B is equal to n2 into k2. That is, A minus B must be in a scalar multiple of n1 and A minus B must be in a scalar multiple of n2 also. Scalar means integer multiple of n1 and integer multiple of n2. From these two equations we can write, as the left hand side of these two equations is same, therefore right hand side of these two equations must be same. Therefore, we can write n1 k1 is equal to n2 k2. Therefore, n1 k1 is equal to n2 k2, but also given that n1 GCD of n1 and n2 is equal to 1. Therefore, n1 and n2, their common divisor is 1. Greatest common divisor is 1, means there is no common divisor in between n1 and n2. Therefore, n1 does not divide n2 or n2 does not divide n1. Therefore, we can say that n2 must divide k1. Means k1 must be in multiple of n2. Therefore, there exists integer k such that k1 is equal to n2 times k. Okay, so this implies there exists an integer k such that k1 is equal to n2 times k. Put this value in equation above, which is a minus b is equal to n1 into k1. Now in place of k1 we put n2 into k2 and we get the new equation a minus b is equal to n1 n2 k. This implies that n1 and 2 divides a minus b. And therefore by definition of congruence relation, we can write a is congruent to b mod n1 into n2, and that is the required. What we have to prove here is this thing: a is congruent to b mod n1 into n2, and the solution of this problem is over. Let us write one remark. If p and q are distinct primes and a is congruent to mod p as well as a is congruent to mod q, then we can write a is congruent to mod p1 into p2. As here p and q are distinct primes, therefore their GCD is 1, and we can use the previous example to show that a is congruent to b mod p1 into p2. P and q are distinct primes and a is congruent to b mod p as well as a is congruent to b mod q, then the result is a is congruent to b mod q1 into q2. That is very simple remark, and we can understand very easily by using previous examples. Now let us write question number 2. For any integer x, show that x square is congruent to 0 mod 4 or x square is congruent to 1 mod 4. Okay, for any integer x, show that x square is congruent to 0 mod 4 or x square is congruent to 1 mod 4. And b is, if x is an odd integer, show that x square is congruent to 1 mod 4. Okay, here we have here we have to write a x square. X is missing. If x is an odd integer, then show that x square is congruent to 1 mod 4. Okay, answer. Here x is any integer, therefore either x is even number or x is an odd number. If x is an even number, then x must be in multiple of 2, and if x is an odd number, then x must be of the type of 2k plus 1 for any integer k. Okay, so either x is equal to 2k or x is equal to 2k plus 1 for some integer k. If x is even number, then x is in the form of 2k, and if x is odd number, then x is in the form of 2k plus 1, because all odd numbers are in this format, 2k plus 1 for some integer k. Okay, k is an integer. Now we take a square of both the equations, taking square of both the equations, and see what we get is x square is equal to 2k square plus, or x square is equal to 2k plus 1 square. Now x square is equal to 4k square, or x square is equal to 4k square plus 4k plus 1. Now you will observe that from the first equation, x square is equal to 4k square, the right hand side 4k square is divisible by 4. Therefore this left hand side x square is also divisible by 4. Therefore 4 divides x square. That means that by the definition of congruence relation, x square must be congruent to 0 mod 4. Okay, from these two equations. And similarly on the right hand side, if I divide by 4 on the right hand side, the remainder left is 1. Therefore we can say that if we divide by, or we can write x square minus 1 is equal to 4k square plus 4k, and then we can say that right hand side is divisible by 4. Therefore left hand side x square minus 1 is also divisible by 4, and therefore by congruence relation we can write x square minus 1, x square is congruent to 1 mod 4. So we have this thing, x square is congruent to 0 mod 4, and or x square is congruent to 1 mod 4. Okay, that is very simple. And let us take question number 3. Find the least positive integer and the greatest negative integer to which 514 is congruent modulo 37. Okay, so to solve this problem we will use division algorithm. So we know that if I divide a number a by n, and if in this division the remainder left is r, then we say that a is congruent to r mod n. So r is the least positive integer such that a is congruent to r mod n. Okay, so in this case also, here a number 514, we divide this number by 37, and we observe that what is that remainder left. Okay, so by division algorithm, see here, the least positive integer to which 514 is congruent modulo 37 is a remainder left when 514 is divided by 37. Therefore, division algorithm is 514 is congruent to 37, 514 is equal to 37 into 13 plus 33. So here quotient is 13 and the remainder left is 33. Therefore, 514 is congruent to 33 mod 37. That is the first part. Okay, now 33 is a least positive integer which is congruent to 514 mod 37. Now we have to find out greatest negative integer which is also congruent to 514 in modulo 37. So for that we just take a difference of 37. Okay, so this shows that 33 is the least positive integer to which 514 is congruent modulo 37, and take a difference 33 minus 37, it gives minus 4, and is a greatest negative integer to which 514 is congruent to modulo 37. So in this way, in this lecture we solved 3 problems, and we will solve more problems in the next lecture, and we let us stop here. For any query you can contact here, and thank you very much.